Okay, in the last video we learned about electron group geometries, where we were looking at how many electron groups were attached and what kind of geometry you get. We looked at like tetrahedral and trigonal bipyramidal and linear and trigonal planar and all that stuff. Okay, but we didn't differentiate between lone pairs and bonds connected to central atoms. In this video we're going to talk about that, but instead of going through every possible detail, because there's a lot, what I'm going to teach you to do is use this table. And honestly, I'm going to teach you by using examples. As far as exams and quizzes, I am content with you bringing this table. I do not want you to memorize it. But I will tell you that for the final, you are not allowed to have this, and I will need you to memorize like the left side. It's pretty straightforward. It's not terrible, but the left side are the ones that don't violate the octet rule, and you will probably need to know those for the final exam, okay, the cumulative final. So let's just try a few examples and see if we can figure out how this geometry stuff works. So, let's literally start with a really easy one. Start with water, okay? So the very first step of this is you draw the Lewis structure. So literally the entire last chapter, I need you to be proficient at that before you even worry about this. So, hydrogen has one valence electron, and there's 2 of those. Oxygen has 6. That only gives us 8 electrons, and everything's shooting for 8. So, we'll see what happens. Hydrogen is way more electropositive, but it cannot be the central atom, so oxygen's in the middle. We can't give the outer guys dots, so the inside ones get them. This already has 2, 4. We have 4 electrons left. Yay, water. Okay. Now, if you draw it like this, that's totally fine. Your Lewis structure looks linear. It looks like a straight line. Everything's symmetrical. It feels like it's great. Okay? Here's the problem. The way we do this is we look at the central atom and we look at the total number of electron groups. So we're not differentiating between lone pairs and bonded pairs. And remember that single bond, double bond, triple bond, and lone pairs, each of those only count as one group. So on this table, if you have one printed out in front of you, it might be a little easier to read, but you go down, look at the total number of groups. We have 1, 2, 3, 4. Okay. So there are 3 options. So the first column says number of electron groups. There are 3 options for there being 4. Okay. And you'll note that the electron group geometry is tetrahedral for all of those. Okay. So it's essentially a variation of this, tetrahedral. Okay. Now what we care about is, of those groups, it is important that you distinguish here, of those groups, how many of them are lone pairs? So there's 1, 2, 3, 4 groups. 2 of them are lone pairs. So you look at this chart, you go down, number of electron groups is 4, number of lone pairs is the 3rd column, and it's 2. And you'll notice it's an A, X2, E2. So you could visualize this as an A, 2 X's, and 2 E's. Okay, so it still fits that other format that we were talking about. And the geometry, some textbooks call it angular, most textbooks call it bent. I really liked this table other than the fact that they said angular. So if you call it angular or bent, I'm ecstatic. Okay, so the geometry would be bent. I'll put angular in parentheses in case you decide you like that one better. Okay? So, what does this stuff really look like? So, it's essentially a tetrahedral, but 2 of the groups are actually lone pairs. They're still repelling and they still shape everything the same. But that's more, this is actually a carbon in the middle, but this is more what water would look like. It is actually a bent molecule, like we're saying. Okay, this is where the name comes from. So it looks like it's supposed to be linear, but it's actually bent. I have no problem with you drawing it like this as long as you can visualize it like this, so, with the help of this chart. Okay? So the idea, of course, is that if you were going to try to draw this accurately, what would probably happen is it would probably look more like this. It'd need to be about 109.5, and there would be a lone pair and a lone pair. And the lone pair, technically, like this one would be a wedge and this one would be a dash. One's pointing towards you, one's pointing back. But the bond angle is approximately 109.5. We'll talk about the fact that these are approximate values in a later video. But let's just try a few more examples and see what happens. Okay. Okay. This is a compound called formate. Okay. So it is not actually an acid. So the hydrogens are not on the oxygen. So this has 4 valence electrons, this would have 2, and this would have 6. So we'd end up with 12 electrons. Carbon is the best central atom. And we would go through the legwork, and there would still be 2 more electrons, and then this one would be too short, so we'd make a double bond. Kind of skipping steps here because I'm assuming that you've seen the other videos and you've seen the lectures on how to do Lewis structures. This would be the structure of it. Okay? So, what we care about is carbon. How many valence electrons does it have? Well, we count 1, 2, 3. Double bonds count as one group. So 3 electron groups, I'm going to start abbreviating everything. And 0 of those are lone pairs. So using this chart, 3 electron groups, 0 of those are lone pair, we get trigonal planar. You'll notice that if none of the groups are lone pairs, the molecular geometry and the electron group geometry are the same. On quizzes and exams, I pretty much only care about the molecular geometry. I can't guarantee that the cumulative final won't for some reason ask about electron group geometry. Okay, but this would be trigonal planar. Okay, so I don't need you, I am perfectly fine with you drawing the Lewis structure like this and telling me it's trigonal planar and I'm happy. But if you wanted to draw this and see what it really looked like, you would have this up, the stuff would all be in one plane, and everything would be about 120 degrees. Single bonds, double bonds, lone pairs, they each push on each other a little differently, so we'll have to deal with that later. But these are, it says ideal bond angles, but it would say that it's 120. Okay. Let's just try a few more to get some practice at this. Okay. How about PCl5? Okay, so phosphorus has 5 valence electrons, chlorine has 7 times 5, would be essentially 40 electrons, which is a lot. Phosphorus is the best central atom because it's farther away from fluorine. We have to attach 5 things to it, so automatically not going to be right angles. But we're learning in this chapter that none of them are really right angles for the most part anyway, so whatever. We give the outer guys their dots first. If you check the formal charges, which I've been kind of skipping that part of the process because I'm more worried about the geometries than I am about the Lewis structures, everything would come out to 0. Phosphorus would violate the octet rule, but it still has a charge of 0. So we have 1, 2, 3, 4, 5 electron groups, and 0 of those are lone pairs. Okay, so what that means for us is 5 electron groups, 0 of those are lone pairs. We would expect a trigonal bipyramidal. I think in the last video I forgot to explain where that name comes from. You essentially form a 3-sided pyramid. So we had the up and down, the axial ones. You form a 3-sided pyramid on one side and a 3-sided pyramid. So trigonal, which is the 3-sided part, bipyramidal, you form 2 pyramids. So the name sounds weird, but there is some logic to it. Okay. Let's try a few more examples here. How about SOCl2? It's actually a really common organic reactant. It's an oxidizing agent used to make double bonds if you have an alcohol. Okay, whatever. So this is 6, 6, and 7 times 2. So that should be 14 plus 6 would be 20, plus another 6 would be 26 electrons. Sulfur is the farthest away from fluorine, so it's the central atom. And what we end up with, I guess I'll go through all the legwork here. We end up with that. That's only 6 electrons used. We have 20 left. That's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We have 2 electrons left, so they go on the center. okay? If you check your octets, this is 8, this is 8, this is 8, and this is 8. But if you check your charges, this is 0, 0, -1, and +1. Because sulfur is in the third row, we're going to force this to violate the octet rule and form another double bond, or form a double bond. So what we end up with is this. And if you check the charges, this is 0, and sulfur would be 6 - 2 - 4 is 0. Everything's 0. This is actually a happy molecule. Okay. In terms of the geometry here, which is the main thing we care about on this one, is we have double bonds count as 1. So we have 1, 2, 3, 4 electron groups, and one of those 4 is a lone pair. So if you look at this, we have 4 electron groups, so it's one of those, and one of them is a lone pair. This would be called Trigonal Pyramidal. Okay. It is a variation of a tetrahedral because it has 4 groups. Like we saw with water, if you rip off 2 groups, you basically are replacing one of these with lone pairs. You can almost just remove the atoms. If we only remove one, because we only have one pair, what you end up with is something that isn't flat. I don't know how to show that on the video, but it isn't, there's a gap under there. But what you end up with is a 3-sided, 1, 2, 3, a 3-sided pyramid. So it's trigonal because of 3 sides, and pyramidal because it forms a pyramid. It's not trigonal bipyramidal because it's only forming 1 pyramid, but there is logic to the name. Okay. So, I mean, I could do examples for hours here, but the idea is that you draw a structure, you do check the formal charges, you violate the octet rule if you have to, you do all the stuff that you would expect with Lewis structures, and then based off of your structure, based off how many electron groups there are and how many of them are lone pairs, you can determine the molecular geometry, which should tell you about the approximate bond angles. I am happy to let you use this chart on quizzes and exams. Please make sure you print one of these off for lecture. It'll make this go so much easier, okay? All right, thank you.